That's right. So if any of you had not seen before what the four-dimensional cube looks like, this is a picture of the four-dimensional cube. Of course, this is not the four-dimensional cube because it's not four-dimensional. But this is a picture of what we like to call the skeleton of the four-dimensional cube. In other words, the points are the vertices of the cube. The edges are the one-dimensional edges of the cube. Any little parallelogram that you see around actually is one of the two-dimensional faces of the cube. And anything that looks like a cube in this picture actually is a three-dimensional cube, which is a face of the four-dimensional cube. So I think it is a good exercise actually in life to stare at this picture and make sense of it. But for our purposes, we don't need to know that this is the four-dimensional cube. What we need to know is that this is the post-set of subsets of a set of four elements. Okay, and that's how I have labeled the sets. And you'll see why I'm drawing this. The idea is that, remember that one way of describing a matroid is to tell you what the rank function is. Okay? I can describe a matroid by its rank function. Rank function. Okay. So, for example, let's look at the matroid of a graph. So the edges 1, 2, 3, and 4. So we know that this is this gives rise to a graphical matroid, whose bases. So the ground set is 1, 2, 3, 4, and the bases of this matroid are all the spanning trees of this graph, which is every pair of edges except for 3, 4. Okay. Now, one way of describing this matroid, here's a very compact way, right? Now I want almost the least compact way possible, which is in this picture. I want to describe this matroid in this picture, and the way of doing it is that I have a rank function. And the rank function takes each subset and assigns to it an attribute. And this is what I'm going to record here. So here's 2 to the e. And now at each dot, I'm just going to record the rank. Okay, so the empty set has rank 0. Then each edge on its own has rank 1, because there's no loops here. So 1, 1, 1, 1. Now, the pairs of edges have rank 2, except for the pair 3, 4, which is a circuit, and it has rank 1. So 3, 4 has rank 1, and everything else has rank 2. Okay. Now, any set of 3 edges has rank 2, because every set of 3 edges is spanning. And the whole set has the rank of the matroid, which is rank 2. Okay. And so here is another description of this matroid. Okay. And now what I want to think about is, okay, so this is the same matroid as this one. And the idea is that this is supposed to be a visual aid for you guys to think about rank functions. You already had to do a proof using rank functions, and I think you realize that it gets messy if you don't have a visual aid, and you can get very easily lost in all the symbols. Okay, so what I want us to think about now is, if I give you the labeling, if I give you the rank function, how can you tell if these red numbers actually constitute a rank function or not? Okay. So what are the local rank axioms?
So I'm sorry, what is the question? We're trying to see if the red numbers constitute
Right, so in this case, I know that the red numbers do constitute a rank function because I showed you the matroid that they come from. Okay? But the question that I want to ask now is, what if I just give you some labeling of 2 to the 4 with these red numbers, and I ask you, do you have a matroid in front of you, or do you not have a matroid in front of you? Okay? Well, what you have to do is check the rank axioms. Okay? And as we saw, you can check either the global rank axioms or the local rank axioms. And what do the local rank axioms say? Well, the first local rank axiom, you'll remember, just says that the rank of the empty set is 0. So that's the first thing you're going to have to check, is that the bottom element should have rank 0. Okay? The second thing you have to check, if you remember, the second rank axiom says that if you go from rank of x to rank of x union something, you can jump it by 0 or by 1. In other words, going from x to x union something in this picture means going from a vertex up through using one of the edges. And so what this second rank axiom says is, if you have an x here, then this is, so if you have an x here, then this guy has to be either x or x plus 1. Okay. So that's the second thing you would need to check in this picture, is that whenever you walk up an edge, you increase by 0 or by 1. Okay. And if you remember what the third rank axiom says, it says, let's say that you start with some set x, and including A doesn't increase rank, including B doesn't increase rank. Okay? So again, you want to think that this is your set x, including A means going up one edge, including B means going up a different edge. Okay? And the assumption is that if here you had rank x, then here you have rank x, and here you have rank x. That's the hypothesis of my third axiom. And the conclusion is that if you do x union A union B, you still have the same rank. But where is that in my picture? If this is x union A, and this is x union B, then the union of both of them is right here. You can see it, for example, if I go from 4 to 1, 4, and from 4 to 3, 4, then when I add both, I just complete the square.
But in that case, when you go to 4 to 1, 4, and 4 to 3, 4, they're not both the same as the rank at 4.
In the case that I'm showing you, this axiom doesn't apply, because you start with a 1, and a 2. So what you're going to look is whether anywhere you see 3 numbers in a V shape that are equal. You see them?
The 2s.
You can't do it with the 1s, but you can do it with the 2s. So for example, it's telling me that if I see a V shape of 2s, then I can complete the square and always see a 2 above. And that's what this axiom says. If I see a V shape, then I complete the square, and this should really look like a square. Well, it should look like a parallelogram because it's kind of a distorted square. But if you have x's in the bottom 3 entries, then you also have an x in the top entry. And that's what axiom 3 prime tells you. And this is kind of the pictorial way of thinking about local rank axioms. Now, I also want to show you what the global rank axioms look like. The global rank axioms say, the first one says that the rank of x is less than or equal to x. So what that means is that on On level k, the numbers are going to be less than k, at most k. Okay. I mean, it's really the only interesting action of the three. The only one that tells me something different is submodularity, and I want to show you what that says. Submodularity says rank of A plus rank of B greater than or equal to the rank of the intersection plus the rank of the union. Okay. So this is an axiom that you had to apply all over your homework, but maybe you had trouble visualizing what this actually is saying. But in this picture, you can see it absolutely clearly, because you can find A is somewhere in this picture, B is somewhere in this picture. So here's the whole set to the E. And you know that A is somewhere in there, and B is somewhere in there. Okay. How are you going to find their intersection? Well, if I give you two guys here, and you want the intersection, what you have to do is see where they meet, where they go down, and you find a greatest lower bound. Their intersection is here somewhere. Okay. And where are you going to find their union? This is kind of the key question. What you're going to do is just complete the parallelogram. Okay? And I'll show it to you here. For example, let's say that you started with 4 and 1, 3. Mm-hmm. Then the intersection is the empty set, and the union is 1, 3, 4. Okay? And this is a parallelogram. Okay? The point being that to go from A intersection B to A, you have to add the same thing that you add when you go from B to the union. So what you're doing is completing a parallelogram here, and that's the union. You shouldn't take my words for this. You should really stare at this long enough until you see it, and it's really a matter of staring at it until you see it. But submodularity really talks about parallelograms in this picture. And what it tells you about these parallelograms is that if you see an A here, and a B here, and a C here, and a D here, then it's telling you A plus B is bigger than C. So this is what global submodularity says in this picture, is wherever you see a parallelogram, the sum of the two level guys is bigger than the sum of the top and the bottom guy. Greater than or equal to. Question, Kim?
It's sort of an observation. Amanda, when she was thinking about the homework, wrote that slightly differently in a way that made more sense to me. It started to make more sense to me, which was that she just subtracted the B and the D. And so let's see if I can get it going in the right direction. Actually, let me subtract the A and the C.
Actually, I want to do it in both ways.
Okay.
So I want to do it like this.
Right.
And I want to do it like this. Okay. So what are these things that I'm putting here? They are the increase in rank. When you go from here to here. You went from A to D, you increased D minus A. You went from C to B, you increased B minus C. You can rewrite this inequality as saying A minus C is bigger than B minus D. No.
D minus B.
D minus B. And you can rewrite this inequality, well, this, the same thing, but if you do it the other way around, you say that B minus C is less than or equal to
greater, no, it's greater than or equal to.
I got this one wrong. Did I? Oh, no.
No. The lower you are, the bigger you are.
Right. And so what this is saying, another way of saying the same thing, is that in a parallelogram, the increase of rank is bigger here than it is here. Okay? So this increase of rank is bigger than or equal to this one. And this increase of rank is bigger than or equal to this one. This is equivalent to what I'm saying. And so that means you can think of a rank function as something that tries to increase a lot at the bottom and can't increase so much on the top. It increases more quickly on the bottom than it does on the top. That's what this is saying. And so this is another property of these rank functions, is that in any parallelogram, the increase goes in this direction. Any questions about this? So I want you to get two things out of this discussion. The first thing is that whenever you're trying to write a proof that involves ranks, involves using submodularity, you probably want to find this proof in the picture. And first you want to sketch in the picture and see what argument you're going to make, and then the symbols will just take care of themselves. And it'll take some practice at first, but I find that a lot easier than getting lost with the symbols. So that's one thing, is this is a good visual aid for rank. Okay. But another thing is that really this completely characterizes rank. And so here again I have another way of thinking of a matroid, is just look at this picture. Okay. Now the reason that I bring this up now is because this is going to let us see how matroids kind of reproduce in a way. So if you have a big matroid, how can you get a small matroid out of it? So here's a matroid. How can you get a small matroid out of it? Well, one thing you could do is just cover this part. And then this is a matroid. Okay. Why? Because if you look at a subcube here, then the subcube still satisfies these three properties. Okay. And therefore, when you take subcubes, you still have matroids. Subcubes of matroids are matroids. So let me pick a cube that is not so obvious, just so you get used to seeing strange cubes here. So for example, let's look at the cube. Do the same one that I did here. So 1 empty set. Well, make sure they fit. So empty set 1, 3, 4. These guys are going to determine a cube, which is going to look kind of like this. Right. 1, 3, 1, 4, 3, 4, 1, 3, 4, and I just copy my numbers. 0, 1, 1, 1, 2, 2, I think this is a 1, So there's a matroid, and I basically showed you the proof already. Because if the big cube satisfies these local rank axioms, then by this geometric description of local rank axioms, it's absolutely clear that that this subcube also satisfies the axioms. So people like to call this the matroid, where all you did was you deleted 2. I deleted 2. This is also a matroid. And I could have deleted 1, and I could have deleted 3, and I could have deleted 4. So that gives me 4 matroids. Or I could have deleted pairs of them. For example, if I came over here and I deleted elements 3 and 4, then I would only keep elements 1 and 2. Okay? And the subcube that I would get is this little square right here, 0, 1, 1, 2, 2. And the square is the 2-dimensional cube. So sometimes you're going to catch me calling squares cubes. Square is the 2-dimensional version of a cube. Okay? So I can do this for any subset of 1, 2, 3, 4. I can just start with 0 and just pick some of these guys and form that cube.
What does that symbol m/2 represent again?
The matroid. So the matroid with that rank function is called m/2. And I'll define that exactly in a second, but that's what we like calling that matroid because we deleted 2. And so it's just like a notation for sets. We put a backslash to say delete. Okay, so there's one submatroid. Now, for example, this guy is a submatroid. Now, can I say that this guy is a submatroid right here? So you forget about this side, and you only consider this part right here. Can I think of this as a matroid?
If you subtract 1 from all of the ranks.
So so it's clearly not a matroid because it doesn't satisfy the first property, which is that at the bottom it should have a 0. Okay, and that's kind of a silly way to fail. But you see it actually does have these other 2 properties. It does jump by 1 or by 0. And it is true that if you have a V with 3 equal numbers, then the top one is also an equal number. So the only shortcoming of this guy is that it doesn't have a 0 here. But then what can we do? We just shift everything down by 1. And we get a matrix. And so this is also a matrix. And so let me draw that one for you. So I had 1, 2, 2, 2. This is a subcube of my cube, and I just need to make some changes. First of all, I just subtract 1 from everything. And I get rid of these guys. Adjustments that I should make? Well, it should have 0 at the bottom, so let me just delete the 4s also. Out, out. Okay. I hope you can kind of see what the remaining thing is. It's the matroid that we were talking about. You just do a little bit of relabeling and you get a matroid. And this matroid also has a name. And by symmetry, if this one is a backslash, then this should be a slash. So I deleted 4, but I deleted it in this funny way. So this is also a matroid.
So does the reversal of the deletion sign here indicate that you have to do some finagling to get it to work? Or was that just happenstance? Notice how the bar is tilted this way, and on the previous one is tilted the other way. I was wondering, does that
Yeah, so
mean you have to do something?
Yeah, so the idea is that here I just deleted 2. And wherever I saw 2 in that post-it, I just didn't look at that element of the post-it. So we call this the deletion.
Right, right,
But here, that's not what we did.
right.
We did something that is similar but a little bit different, and this is called the contraction.
Okay, thank you.
And so now I'm actually going to define these things for you. But I think it's better if you... I mean, now you know what I'm going to define, and so now you're actually going to understand these definitions. So, definition. Or maybe I should say, let M be a matroid on E. And take any subset of E. Okay? I'm going to define the deletion, I'm going to define the contraction. So, definition. The deletion of T from E is the matroid. What is the ground set of the matroid if I delete T? Well, I had E and I deleted T, so it's the matroid on the set E minus T with rank function now this is called M backslash T. So what is the rank function of this guy M backslash T? What is the new rank of X? We're going to think of this as the old rank function, and this is the new rank function. So what is the new rank of a set here? It's exactly what it was. So it's exactly what it was. Okay. So I specify the ground set, I specify the rank function, and I proved to you already that this rank function actually is the rank function of a matroid. So this is a matroid. Okay. And now the contraction of T from E, and we write this contraction M slash T is the matroid. What is the ground set of this guy? Well, here I contracted 4, and my ground set was everything except for 4.
Yeah.
So this is also going to be a matroid on E minus T. You just have to say what its rank function is. So what is the new rank of some set X? For example, what is the new rank of 2?
It's the rank of that X union T.
So so
minus 1.
I have to look up what the rank was, but you see, in going from here to here, I have to add
The rank
my
of-
4.
Yeah.
'Cause I deleted t. So when I want the rank of 2 here, I want the rank of 2 union t over there.
Yeah.
If I want the rank of x here, I want the rank of x union t over there.
So it's rank of
So it's the rank
X
of
union T
x union t in the matroid.
minus
Subtract 1.
minus
But we made another correction, which was to
rank of T
uh,
minus rank of T.
to shift the rank function so that it starts at 0. Now, what did the rank function used to be here?
1.
What did I subtract? In this case, I subtracted 1
Yeah, you're talking about
because I contracted 4.
4 had rank 1.
But for example, if I had contracted 1, 4, if I had contracted 1, 4, then I would be looking at this guy right here,
yeah.
which starts at 2. And so I would have needed to subtract 2 from the rank function, not 1. Okay? So when I subtract, I don't subtract 1, I subtract the rank of the bottom guy here, which is t. So that's it. Now, the way you're normally going to see this in a book, they might tell you the deletion is this, the contraction is this, and then they might give you some proof for why these are rank functions. Well, really what the proof is going to be is kind of what we're doing, but I think it's more helpful to see it in this way. And again, you should, if you don't see this right away, why this is what I should have written, just stare at it until it clicks. But really, that's exactly what I'm doing. So this is the mathematical version of the two corrections that I did here. The black correction of getting rid of t, and the red correction of getting rid of the rank of t. Okay. So these are two ways of getting from a bigger matroid to a smaller matroid. Okay? And as you can imagine, these are pretty fundamental concepts. And what you should be thinking here is that in mathematics, it always happens that whenever you define a structure, you're interested in its substructures. So if you define a vector space, then you care about the vector subspaces. Right? If you have a group, then you care about the subgroups. Or if you have a field, you care about the subfields. And basically, that's what we're doing here, is saying what are submatrices. What are submatroids? In other words, what are the matroids that are living inside a matroid? Okay. I just showed you this big picture over there is a matroid, and these are some of the matroids that live in there. The matroids that live inside your matroid. Well, the deletions live inside the matroid, the contractions live inside the matroid. Now, what else lives inside the matroid? Think of something else. Which subcubes are the deletions? If you look at this geometrically. For example, this subcube is not a deletion, right? And the reason is that it doesn't start at the empty set. So if you want to know which the deletions are, they're the ones that start at the empty set. So there I define a bunch of subcubes. The ones that start at the empty set are the deletions. Which ones are the contractions? It's not as immediately obvious, but if you stare at this long enough, you're going to see that they're the ones that end here. The ones that go up here, start here, and are hanging down, are the contractions. So what else should I be considering?
Ones that start in the middle and end in the middle.
Between. I mean, nothing is forcing me to be growing from the bottom or hanging from the top. I can look at any thing inside here, and I'm going to get another matroid. And so, what's a matroid that I haven't defined yet that lives inside this one?
2,
Well, so many choices, but 2,
1, 2,
2,
and over to 1, 2,
1, 2.
and up to 1, 2, 4, and down to 2, 4.
I mean, you could just even say
There's a cube, right? Happens to be a two-dimensional cube. So that's also a matroid. All you have to do is take care of the things that you need to take care of, right? I mean, again, you don't start at rank 0, so remove that. Your ground set is not. I mean, you don't start with the empty set, so remove that. But these things can be fixed. Okay. Now, if you think about this blue matroid can be obtained as a. You start with a matroid, then you take a deletion, and then you take a contraction. How is that? Well,
Start with that cube.
how to draw this in a way that I won't ruin my carefully crafted 4-dimensional cube. I think I won't need this anymore.
Can you leave the graph?
Yeah, I'll leave the graph. Maybe let's go here. Okay, so let's try to look for that blue matroid. So that blue matroid certainly looks like it lives inside our black matroid. Okay, here's the big thing. Then here's my blue matroid. And what I'm claiming is that this blue matroid I can obtain as first deleting some stuff and then contracting some stuff. You see how to do that? Well, what I'm going to do is
Delete 3 and contract 1.
so this is the picture that I want to obtain.
I'm sorry.
What I'm going to do is
Contract 2. Yeah.
start with my big matroid. Okay. Then I'm going to delete what?
3.
I'm going to delete 3. In other words, I'm going to go to this guy right here. Okay. So my black matroid is my matroid M. My red matroid is, what is it? M delete 3. Okay. And now the blue guy is hanging from the top of that one. So here's the red one. And now how do I get from the red one to the blue one? Well, all I have to do is notice that this guy is 1, 2, 4. And I want to keep only 1, 2, and 4, so what I'm doing is I'm contracting. Wait, what I want is 1 and 4, so I'm contracting 2.
Yeah.
In other words, this guy is delete 3 and contract 2. And so
Federico, the matroid matroid backslash 3 is you just eliminate all the vertices that have a 3 in them?
Right, so the first thing I did is eliminated all the vertices that have a 3 in them. So I'm left only with the 1s, the 2s, and the 4s. In other words, I'm left with the cube whose lid is this blue guy. And then I'm just deleting the bottom floor of that cube. And so this is how you obtain the blue guy as a deletion and then a contraction. And so probably what I should do when I define submatroids, if I want to let the blue guy be a part of this game, I should also let a submatroid be a deletion of a contraction. Or rather, a contraction of a deletion. But if I'm going to allow contractions of deletions, then I better allow deletions of contractions, and I better allow deletions of contractions of deletions of deletions of contractions of deletions, right? I mean, if you want this to behave well, and so when I talk about a submatroid, I really want to say, you start with a matroid, you delete things, you contract things, delete, blah, blah, blah. See what you're left with. Now, that would be a horrible definition if it wasn't for the lucky fact that deletion and contraction commute. It's a nice surprise. What's my proof? Well, let me just do this in exactly the opposite way. So here's the matroid, and I wanted to build this blue guy, right? And I said, okay, let's first delete and then contract, but I could have done it in the other direction. Just said, okay, first I'm going to look at the matroid that is hanging from the top and ends here. So that's this guy right here. Okay, what is the name of this matroid?
M contractor.
It's the matroid that goes from 2 to the top. So this is M contract. This is the other thing you're going to see me mess up for the rest of the semester: deletions and contractions. It's very important that you stop me whenever you see me make this mistake. Deletions are like deletion of set, contraction are the other direction. So first I contract 2, and then I take the contraction, and now my blue matroid is living in the bottom of it, so it is a deletion of this guy. So my blue matroid is M contract 2 delete 3. Okay. So what did I just prove? Now, of course, you have to actually write down what it is that we proved and put it in math words, but this is really the proof. Proposition, deletion, and contraction commute. So you can either delete first and then contract, or contract first and then delete,
So that
and
means
you don't
we
have a
can
problem.
Represent any submatroid as a single deletion followed by a single contraction. Or
Well, not yet until I prove that deletion commutes with the deletion. In other words, that if I delete S and I delete T, then it's the same as deleting them both. And it's the same as deleting first T and then S. And the same for contractions. I need to prove that the order of contractions is not really important, because if you contract some things and then contract the other ones, it's the same as contracting all of them at once. Proof? one of these things that they call proof by picture. Well, here's the proof by picture of the first one, which is the hard one. The harder one of the three. And it's actually a good exercise for you guys to draw the pictures of the other ones and see why they are true. Okay? But this is great news. Great news. Because that means that if you started with a matroid and then you decided to delete 2, contract 3 and 5, contract 9, delete 6, contract 4, that means you were really wasteful in operations, because you could have just first deleted everything you meant to delete, 2 and 6, and then contracted everything that you meant to contract, 3, 5, 9, and 4. 3, 4, 5, and 9. Okay. Or the other way around if I wanted to. First contract 3, 4, 5, and 9, and then delete 2 and 6. Okay. You might be a little bit uncomfortable with the fact that I didn't put parentheses here. You're used to seeing a parenthesis here. And the only reason that I don't put it there is because these things commute, and so it doesn't matter. These are two operations that you can tack on and do them in whatever order you want. So that means that my horrible definition of allowing deletion, contraction, contraction, deletion is actually not so horrible. All I need to do is allow you to delete ones and contract ones. Definition: a minor of a matroid is a matroid of the form M. You delete something, you contract something.
Have we completely answered that question up there?
This is what people consider the notion of submatroid, minor. In the literature, you don't ever see the word submatroid. The word that you see is minor. So you won't really see this, but you'll see the word minor. This is the definition. And you might want to think of this as a deletion and then a contraction, or if you're comfortable enough with the picture of the cube, then you don't even have to think about it this way. You can just say it's any subcube of my cube. And it happens that I can get it as a deletion and then a contraction. But an equivalent definition is saying a minor is just any subcube in there. Okay?
So here's my question, because I know we're going, which is, so in graphs we have this, we can delete an edge, or we can contract an edge. And the examples you did makes it look like if my matroid was graphical, these things are working the same way. And my question is that true?
That's a great question. As you know, a good part of matroid theory is inspired from graph theory. And in graph theory, we saw that we have notions of deletion, which is that you just delete the edge of the graph, and contraction, which is what you discovered in your homework. Contraction means merging two vertices. Okay? And this is good terminology because deletion and contraction in graphical matroids are exactly the deletion and the contraction of the graph, which is good news. Maybe the last thing that I'll say is, why did I restrict here to S and T having empty intersection?
Because you can't delete and contract the same thing.
The point is that, for example, this one makes sense if S and T had a common element. Then you start with a matrix, then you delete S, and then when you go to delete T, you already deleted the common element, so this expression doesn't make sense. The same with contraction. I mean, the ground set of deletion and of contraction is E minus the set, and so these expressions only make sense if S and T are non-empty. So this isn't some technical condition. only in some cases this is true. This is true whenever these expressions are defined. Okay, I'll stop there.
Yay. I need motivation.
It's cool because you don't have to start.
Yeah, me too.
It's ridiculous. I have one in my house and I keep breaking things.
Yeah. That's probably why I don't want to keep them there.
I used to practice juggling in orange when I was young.
In orange?
Yeah. Because they didn't sell these fancy balls, you know, the now.
Yeah.
But I think in orange is easier actually. It's heavier.
I almost bought an indoor ball too, but I was like, that's too much.
This is good. I'm glad you're giving business to more people.
Yeah, I really am. They're selling the tickets there too.
For the game?
Yeah. Did you get my email? Got it? Did I send the email?
I don't think I got it.
They're selling tickets there. They're $33 for the cheap ones. And he
33?
claims that that is cheaper than if you buy it on the internet with all the service fees and stuff.
Well, I believe that.
And I don't know if the box office is open at the Coliseum because there's no games right now. Or no, there's, well,
Is it at the Coliseum?
yeah. And so the $33 ones are like, they're dead really high.
I like that. Then you can see the game. I don't care to see their faces, you know.
Expected, right? I want to look at them.
This is what always pisses me off about you don't want to look at the Ecuadorian team. Come on, it's Italy coming, but we're talking. It's Colombia we're talking about.
No, the Alta said the Ecuadorian team's cuter than the Mexican team.
Okay.
It's all relative. Well, she said they were cute.
I don't believe it.
What were you saying?
Forgot. Oh no, this is what annoys me about watching games in American TV, that they always just zoom in on the faces to try to make it very dramatic, and you just can't tell what's
You
going
don't
on in
know
the game.
what happened. I know. I gotta be able to watch and get hints on positioning and, you know.
It's really eye-opening. I remember the first time I saw a game, it was actually live because we didn't have